So I have a good mix from between PhD students and master students. Hopefully this will be a useful course, and I'll do my best to make it an enjoyable course. So I'm Haitham Taha, and I'll be thrilled to be your dynamics instructor this full quarter. I'm starting here in my title by saying that the dynamics is the science of everything, because it's indeed ubiquitous. You find it in airplanes, cars, submarines, bridges, skyscrapers, roller coasters, space shuttles, tanks, you name it. We have fluid dynamics, structural dynamics, biological dynamics, molecular dynamics. It's in every single discipline nowadays. It's indeed ubiquitous. And for this ubiquitous science, how old is it? Anybody want to guess? How old is dynamics? Maybe the last century, 17th century is famous of dynamics. Well, for the lack of historical records, it goes back to Aristotle. So we can trace some excerpts, some quotes from his work on dynamics. I'm sure that ancient Egyptians used dynamics, at least to build the great pyramids, but we don't have records. And for this, if we go back to the time of Aristotle, he developed what he called the law of powers. So he said, whatever is a motion, there is a force. So in our language nowadays, it can be written as force is proportional to velocity. If you want to initiate a motion for a body, you need to apply a force. This is understandable. But if you want to keep this motion, you need to keep applying force, which is not correct, right? So, and by the way, the ancient mixed the mass with the weight. So they used them interchangeably. And using this incorrect law, he came up with incorrect results, like the falling time is inversely proportional to the weight of the body. If a heavy body falls, it falls faster. So which doesn't make sense. We know it nowadays. But fortuitously, luckily, using this incorrect law, he came up with a correct law for the liver. They have machines at the time. They have the liver, screw, some machines. And for the liver, he came up with this law, which is what's gained in force is lost in velocity. Multiply the weight with the velocity for each one of them, you get the equilibrium, and this is indeed correct, and it looks like the origin of the principle of virtual work, or in the middle, the early pioneers, they called it the principle of virtual velocities, which is the force times the distance, right, in the direction of the force, or the velocity in the direction of the force. They must equal each other for equilibrium, the principle of virtual work, which we will study in detail during this course. But in fact, this was not, he came at this law just by chance. He said, well, okay, for equilibrium, the cause of the motion, which is the force, should be in balance. So the cause of the motion here should balance the cause of the motion there, and because for him, the cause of the motion, the force, was proportional to velocity, so he simply equated the two causes of the motion, right? Fortuitously or luckily, the velocity that this guy would move by if there is no equilibrium is proportional to the length. It's omega r, right? So if you just remove this guy by a proportionality to the length, you immediately recover the correct law. So his law was indeed correct, but using an incorrect hypothesis at the beginning. Interestingly, he believed that there is a natural place to which all moving objects, they tend to. So if you leave any subject, it will just go to this natural place, which he deemed to be the center of the earth. So he and his disciples classified motion to natural motion and violent motion. In the natural motion, the object is moving towards the natural place. And if it's in the natural place, there is no motion unless you apply a force, which he called the violent motion. To us nowadays, it looks like an unforced motion. Indeed, he observed acceleration. When you leave a body, it comes down accelerating. and according to this law, it doesn't, it doesn't conform with this law anymore. So he said, no, the heaviness, which is the source of the motion, which provides velocity, this heaviness increases as the body goes towards the earth, okay? So as you can see, there are a bunch of incorrect laws, but the thing is, this at that time made sense. So to an unsophisticated observer, if you want to push a body and the body is heavy, you need to push harder, right? And if you want this body to move faster, you need to push harder and harder, right? So this made every sense to an, like I said, unsophisticated observer. And again, he used this law to come up with rules for most of the machines at that time. The lever is one of them. But it had contradicted many other observations. And whenever they encounter an observation and a contradiction, they reconcile it with the exception. They say, this is a special case. This is an exceptional case. So the first thing is that astronomers, they observe heavenly bodies in a different way. He said, no, they don't follow the same rules as ours. Every heavenly body is a divine by itself, moves according to its own nature. What about projectiles? We just throw this guy, it keeps motion in the air without you keep applying force. This is clear contradiction. He said, no, air is a special case. Air conserves the impulsion. So whenever they encounter a contradiction, they don't go back and revise their principles, but they say this is a special case, interestingly. They have very dogmatic opinion. He came up, interestingly, with the composition of motion in a correct way. He said if you have the tendency to move in this direction and the tendency to move in that direction, the net motion will be on the diagonal of the parallelogram that is composed of these directions. This is very interesting. Of course, it's correct. And this is very interesting to me. He said there is no vacuum. Why? Because if there is a vacuum, there is no natural place in vacuum, and this will hold. This is, again, quotation from his work, translation from Latin. So look at this. It will either necessarily stay at rest, or in motion will move indefinitely unless some obstacle comes into collision with it. This is indeed Newton's first law. So this guy came up with Newton's first law before Christmas, but he refused to take it. Why? Because it opposes his thing. So he said, what's the consequence? The consequence is there is no vacuum. That's indeed very interesting. His school of thought lasted for more than 2,000 years with prejudice against anybody who is against these ideas. And we can see in the history words like Aristotelian. Are you Aristotelian or not? Or schoolmen who defend the school of thought. This delayed the development of mechanics for, like you can see, thousands of years. Still with the Hellenic era and Archimedes before Christmas still, you can say he is the first true mathematician in the following sense. If you read his work, it's indeed in the following structure: axiom, proposition, proof. This is the very same structure that you see in the mathematics papers nowadays. So this was long time ago. He was the first to realize that the effect of a weight at a distance from the fulcrum for a lever is just PL, so he's very close to come up with the concept of moment. He came up with the concept of center of gravity, CG of composition of bodies, CG of some common shapes, and to me, which is very, very interesting, CG of a parabolic segment. I don't know if I can do it here, but maybe I can do it in my laptop. So I'd like to show it to you in a second. So actually, here is his work. Look at this, before Christmas, okay? So you have whatever here X is. Okay, I'm not that good at drawing at all. And he has a parabola and a line. Okay? And he wanted to determine the area, not only the area, but the CG of this parabolic segment. This is a This is not a trivial problem even nowadays, right? You need to sit and do, half a page of geometry to do it and calculus, right? His solution was very interesting. I'll give you the final result. He said, okay, you need to get the CG of this area, parabolic segment, draw a line tangent to the parabolic segment that is parallel to your line. So this point, actually the CG is along this line. So immediately gives you the x coordinate of the CG. It's just the point that has the same slope on the parabola as the line. Moreover, if this is P and this is V, your CG is here with PG is 3/5. Done. That's amazing. So you would see here that actually René Dugas, who wrote the book History of Mechanics, from which I got most of these things, he said he determined the CG of this parabolic segment by means of an analysis which is a milestone in the history of mathematics. And more interestingly, there is a 2015 paper extending the same concept. You can just go and download it and look at it. It's very interesting. And of course, all of you can recall his work on floating bodies, which we had in the high school, right? The rho VG kind of thing. So this was the Hellenic era, what we call the Aristotelian mechanics. And I'll do a huge leap in history. So this is Kepler, now in the 16th century. He is still Aristotelian. Everybody has to be an Aristotelian, even Galileo himself. So, but he was a tireless calculator, and we're going to see how. Moreover, more importantly, he rejected every law that allowed the slightest imprecision. He is famous of his 3 laws, if you guys remember. The first of which is that the planetary orbits about the sun are elliptical, with the sun is at one of the 2 foci. And because it's an before him, it was not elliptic. The belief was it's a circular orbit with some offset. Because it's not circular and it's elliptic, so the speed of the planet is not constant, right? It accelerates and decelerates, so the angular velocity is not constant. And the rule or the law that he came up with is that this line from the sun to the planet sweeps equals areas in equal times. And these are all empirical laws. They are not derived. Okay, so empirical laws from measurement. The final one is the period of the orbit, the time to complete one cycle, squared is proportional to the semi-major axis. Remember, this is an ellipse, so the ellipse is defined by major axis and minor axis. The semi-major axis, A, so the t squared is proportional to a cubed. In other words, this rule relates the time, the periodic time, with the dimensions of the orbit. In fact, the first law, this guy, the ellipticity of the orbits, it came up second chronologically. And it has a little bit interesting story. So you can see here, this is the story of how he came up with the ellipticity of orbits. There's something called Mars opposition. So there are some times where Mars, Earth, and Sun, they are on the same line, with Mars being opposite to Sun. Okay, this is what we call Mars opposition, opposite to Sun. And it happens almost every couple of years. You can see here 10, 12, 14, this is 2010. These are exactly the same things. 2010, 12, 14, 16, and so on. So these are the locations of the Mars opposition. So his teacher, they had a table for the locations of the Mars opposition since 1580, and this was 12 locations, okay, until his time. Through his calculations, he accounted for all these oppositions within 2 minutes accuracy at that time. And to do that, he repeated the calculations 70 times. This is why people call him tireless calculator. Okay, he accounted for all these things within this very good accuracy at that time, but the other positions of the Mars, other than these particular Mars oppositions, they are invalid. The longitudes of the other positions, they are not valid. And he tried to reconcile this, and the only way is that the orbit has to be elliptical. So he abandoned the circular orbit argument, and he stated his first law. And this is a very interesting quote from René Dugas' book. He said, "Fortunately for theoretical astronomy and for the development of Newtonian mechanics, Kepler reduced to neglect such a disparity between calculation and observation." This is a very important quote, because you guys are first year in grad school, and you will certainly encounter deviations, disparity, inconsistencies, whatever you want to call it, for sure, in your research. And you always have one of two options. Just sweep it under the rug, right? Or not in a malicious way. You can say, well, maybe I did something wrong here, something wrong there. The phenomenon or the principle is not wrong per se. Like Aristotle was doing, right? This is a special case, right? This guy did not abandon it. And if you do not abandon it, there is an opportunity there. What I'm trying to say is that you will certainly encounter deviations and inconsistencies between your calculations and observations. You will certainly encounter. There is a chance, whenever you encounter these deviations, there is a chance that there is a big discovery there. Or a discovery, not necessarily big. And the discovery comes with its own joy anyway, even if it's not that big. Now, jumping to Galileo, this statement from Lagrange's work, again a quotation. And he says, "This science, meaning mechanics, we owe entirely to the moderns, and Galileo is the one who laid its first foundation." He is the one who emancipated dynamics from the Aristotelian thing. He himself started as Aristotelian. He had to. But at the end of the day, he corrected for the Aristotle points of view. So something to admire about Galileo, at the age of 25, he was the chair of mathematics at the University of Pisa. That's okay. I mean, it's admirable. To me, what's more admirable is that he is the first experimentalist. Nowadays, if you are a theoretician, you will just brag and tease experimentalists and say, you guys do not come up with original ideas or fundamental principles. We theoreticians do. Computational people, they will say, you guys cannot produce as accurate things as we do, computational folks. And experimentalists, they do the same. But for this guy to be the chair of mathematics and experimentalist at the same time, this is really admirable. By the first experimentalist, I'm saying he is the first true experimentalist, where he inferred facts from physical observations, experimental observations. He came up with the concept of repeating the experiment to see if the results are reproducible or not, and what's the deviation between each measurement and the other. He studied, like everybody, all the machines, the lever, the lathe, and he, for the lever case, he came up with the concept of the moment now, more clearly. He studied equilibrium on an inclined plane, a very interesting problem, the falling bodies, projectiles, many others. So for the motion along an inclined plane, he came up with now what can be said as the basis of virtual work, principle of virtual work. Because he said, it's not any velocity that you multiply by. It has to be the velocity in the direction of the force. Now you're talking about dot product, and it's indeed the work, right? So for this, he said, so for the weight, for example, as a force, it's only height that matters. Okay? So this ball, for example, on an inclined plane, will come to this distance and then go up to the same height. And this is a physical observation. He discovered that the distance of travel goes by the time square. This was not known at the time. And also that there is a uniform acceleration. The velocity is not constant when you fall, it's continuously increasing. And you might think, well, I mean, this is enough to get this thing right away. Yeah, because now we know the rules of kinematics. Back then, there is nothing known, right? So he came up with this. This is a physical observation with an experiment that he repeats like 100 times, and I'm not exaggerating. And this is another experiment to come up with this fact. These are facts. Okay, it's not like he derives. Actually, he derived this. When he came up with a physical observation, he tries to demonstrate it mathematically. When he demonstrated this thing mathematically, he got it incorrectly. But fortuitously, he got the right thing. At the end of the day, he's trying to, we are engineers, right? So if you tell me a physical observation and, okay, this is a fact, and you want to come up with a physical explanation for it, for sure I will come up with a physical explanation. And we might ask, well, do you want to try it or do you want it wrong? Do you want to try it or do you want it left, right? We can always come up with physical explanations. But the facts are facts. This is very important. I don't have time to have all the quotations, but if you go and read the work, indeed, he alluded to the concept of continuous acceleration. The velocity is continuously increasing. And he almost said the word infinitesimally increasing. So he is kind of invoking calculus, infinitesimal calculus, the concept of acceleration itself. And this is an interesting rule that he also observed, experimentally and proved mathematically, that the time it takes to travel a certain distance by a uniform velocity is the same as a body falling with a uniform acceleration if you travel with a velocity that is half the final velocity. So he's almost, you can say that he almost came up with kinematics. And this is from his own work. When this observation had been repeated 100 times, this is what he's saying. The distances traveled were always found to be in the ratio of the square root of time. And this was true whatever the inclination of the plane. This is very important. Just look at it. These guys knew nothing at that time, in the sense that they were trying to infer both dynamics and kinematics simultaneously. It's very hard to do it. It's very hard to do it. At the first statement, distance goes with time squared. This is kinematics. This is a final result of the ensuing motion, right? But this thing, now, what is its relation with the inclination of the plane? Well, the inclination of the plane affects the component of gravitational acceleration. This is dynamics. Has nothing to do with kinematics. Of course, they have to be independent. And they had to, arrive at these rules themselves. And then he continues. But the duration of the fall is different, depends on the inclination. For sure, because the duration of the fall is a dynamics principle, right? It's dynamics quantity, has to do with the acceleration, so it depends on dynamics. That was Galileo, and still with him. I just want to tell you guys how he measured time. I mean, at that time, they can measure long time durations, right? Maybe by sunshade or whatever. But we're talking about experiments. So he had a ball on an inclined plane, and this ball, for example, will take few seconds. How you can measure this time to relate that the distance goes by time square, all these accurate representations. This was his way to measure the time. A tank with an orifice at the end, and he collects this water during the excursion of the fall, and after the fall he takes it and just weigh it. And now this weight of the water represents time, right? Because we have a constant velocity here, so we have a constant m dot. So the m represents time, the integration of m dot, right? Anybody remembers the rule of this thing? V equals square root 2gh. You remember the name of the guy, and after him it was named? Anybody remember? Torricelli. This is Torricelli's rule. Torricelli was one of the disciples of Galileo. And this is the most important thing from Galileo, his principle of inertia. He's saying that if you're on a horizontal plane, you can keep moving or stay at rest without applying force. So now he marks a clear distinction from Aristotelian mechanics. That's it. And this is almost Newton's first law, right? He worked on projectiles, and look at that. This is also very interesting. He did composition of motion like Aristotle, so he benefited from Aristotelian mechanics in this sense. And he has his own principle of inertia, that if you're moving horizontally, nothing will happen. You'll keep moving with the same velocity. So these two principles, combining them together, he solved the problem of projectile. So a projectile can be regarded as composition of two motions. The first, according to the principle of inertia, is just moving uniformly with a constant velocity. And the second is falling vertically, and he knows that the distance goes by time squared for a fall of a heavy body. The result is a parabola, and this is his own words. Animated by the motion, composed of a uniform horizontal motion and a naturally accelerating falling motion, the projectile describes a parabola. So, like we said, Galileo really emancipated dynamics from Aristotle's authority. Then came Huygens. He was between Galileo and Newton. He came up with the concept of cycloidal clocks. What is a cycloid first? This is very interesting again. Cycloid is this curve, this black curve, that you can develop by a point on the rim of a disk that is rolling without slipping. As this disk is moving, rolling without slipping, this particle will draw this curve. This curve we call cycloid. It has very, very interesting characteristic that if you start balls at different locations on the cycloid, they will all come at the bottom at the same time. Interesting. So he said, okay, if we now, given this interesting property of the cycloid, if we use this curve to construct a pendulum, which we call cycloidal pendulum, this pendulum will always have constant period irrespective of the amplitude. The circular pendulum that we know, if you move from 60 degrees to 60 degrees, it has certain period. But if you move from 30 degrees to 30 degrees, it has a different period. So the period depends on the amplitude. This guy knows, right? Because they all fall to the bottom at the same time. So now you have a clock whose period, now you can measure, time accurately. You have a clock, and the king actually at that time ordered of manufacturing 3 of this clock for a journey to Madagascar. He proved it via 15 propositions, 15 theorems. Of course, this is not his relation, but he relates the period to the time that it will take for a vertical fall. He stated clearly the principle of inertia. It's not only along a horizontal plane, it's whatever. Any body in motion tends to move in a straight line with the same velocity. Please remember this thing, okay? We will come to it very later in the course. Straight line with the same velocity, the constant velocity, as long as there is nothing to, oppose it. So this is Newton's first law, right? Which is nothing but Galileo's principle of inertia stated in a clear way. He has his contribution in kinematics as well. And finally, he discovered what we know as the centrifugal force. And this is an interesting thing. So if you have a rope, and at the end of this rope, you attach a ball, anybody, and you rotate the thing. Keeps rotating as long as you're pulling the rope, right? The rope is under tension, meaning that it's carrying a force. The force in the rope is to the center. And if it's carrying a force, it means that it's balancing a force that is outward, right? Which is what he called centrifugal force. Well, this is just an idea. How can we make sure that there is really a force? Okay, if you break this rope at any time, what will happen? The thing will move tangent to the circle, right? Okay, so if this is the circle that you're supposed to move with, if the rope is there, if the tension is to the center. and this is the tangent. This is what the body will do if you just break the rope. Okay, so because the rope is broken and I'm not pushing it anymore, not pulling it anymore, right? It moves in this direction and not in that direction. So let's see. Remember, this is motion with constant angular velocity, okay? Which means that the theta goes linearly with time. So theta can represent time now. Okay. So at this instant, I'm supposed to be here, I'm a little bit there. At this instant, I'm supposed to be here, I'm a little bit there. Let's consider that I am at these intersections. This is the distance along the radial, right? How this distance along the radial changes with time will give you an indication if there is a force, if there was a force or not, right? What would be an indication if there is a force? How do you want to see this distance varying with time? Linearly, quadratically, cubically? What do you think? If there is a force existing, the distance should change with time in what manner? Quadratically, with time. But we said that theta represents time. By geometry, you can do this in a minute and really prove that this distance grows with theta quadratically in theta, for small enough theta, of course, which means quadratically in time, which means that there was indeed a force in the radial direction, okay? This is his way of demonstrating the centrifugal force, and via experiments, he showed that it's inversely proportional to radius for a constant speed, proportional to speed squared for a constant radius. Not only that, he even related it to gravity. So he said, if you are moving in a circle, radius r, with a velocity that you will acquire when you fall vertically from a distance r/2, the centrifugal force will be exactly your weight. That's interesting. So usually scientists try to come up with the biggest three names in mechanics. So let's come up first with the biggest name in mechanics. What do you think? Whom do you suggest to be the most well-known person in mechanics? Newton, right? If you're a good high school student, you will certainly say Newton, for sure. That's right. And just to continue the commentary, scientists choose three names. So Newton, for sure. Galileo, right? Now we can appreciate why Galileo, because he is a hallmark in the history of dynamics. Before him, there was Aristotelian mechanics, and after him now, we can do whatever we like. We are free. And the third name is Einstein. And the very last lecture, we will try to appreciate why Einstein is as great as Newton and Galileo. Some people actually, they debate if Newton should be, should get that honor. Because the field is named after him, Newtonian mechanics, right? We'll discuss this now, but at least he organized the principles of dynamics. He published the very well-known Principia, which is, this is in Latin. The English version of it will be Mathematical Principles of Natural Philosophy, 1687. And there is an English translation for it, by the way. There is a commentary by Stanford people on it, in which he defined in a very clear way the concept of mass. Remember, before there was a confusion between mass and weight. Now it's clear, although Huygens alluded to the concept of mass, but you can see it very clearly in Newton's work. Definition I, this was the first definition, the concept of mass. Definition 2, quantity of motion, which is momentum. Definition, I don't remember, 3 or 4, impressed force, which is the applied force. And actually, one of his definitions was the centripetal force, which I really like, because I'm not convinced of the fact about the centrifugal force. I don't like it for some reason, and I feel it's very confusing, the centrifugal force. Because the way we learn the concept of centrifugal force in the baby days is that if a body is rotating, right, have a circular trajectory, then it experiences a force that is centrifugal outward, right? I don't like this explanation because it's not quite right. This is what is exactly correct. Well, at the beginning, the body is moving in what direction? At the beginning. Anybody should be moving in what direction? In a straight line, okay? This is very important. Anybody should be moving in a straight line. If you want this body to move in a circular trajectory, then you need to apply a force towards the center, which is what we call the centripetal force. If you don't apply this force, the body will not revolve under its own, right? It would just fly off. And this is exactly Newton's explanation. He said the centripetal force is the force that pulls the body towards the center. And he said, I'm quoting, this is why I call it centripetal. Because otherwise, again, I'm quoting, the body would fly off. There is no such centrifugal force. It's a fictitious kind of thing. He is very famous of his 3 laws. As we have now seen, his first law is nothing but Galileo principle of inertia, right? Anything should be moving in a straight line with a constant velocity or stay at rest. The second, the change, right? The alteration, the change quantity of motion, which is the mv. The change of momentum is proportional to the motive force, and it's in the same direction. Doesn't say F equals ma, and indeed Newton did not say F equals ma, okay? Indeed, Newton did not come up with the concept of acceleration dv by dt, because at that time the calculus was not that mature. But he can think of the change, and he doesn't even say the rate of change. There is no rate at that time. It needs calculus. Okay, so Newton did not say F equals ma. He said F is proportional to the change in mv, okay? Didn't even say equal in his statement of the law, but in his work, he took the equality. And we will comment on that in a moment. The third, you all guys know, so every action has a reaction that is equal in magnitude, opposite direction. Let's ponder a little bit on Newton's laws, particularly the second one. To me and to most of you, this is the way how we learn dynamics. And actually, I'm quoting from Lagrange. He is clearly describing how we learn dynamics in nowadays, although this was a long time ago. He's saying dynamics is the sign of accelerating or retarding forces and the varying motions which they must produce. This is dynamics, right? You apply a force, there is an ensuing motion. This is the science that has to do with this. This is how we learn dynamics. So for us, high school, undergrad, or whatever, a typical dynamics problem, given forces required the motion, the ensuing motion, right? This is how we understand dynamics. And how we do it? Well, we apply Newton's second law, F equals ma. We're given the force, as we said, and we're given the mass of the object, so we can get the acceleration. And then dynamics is done, we go to kinematics. We integrate the acceleration once to get velocity, we integrate the velocity one more time to get the distance, how the distance evolve with time. And everything now is solved crystal clear, right? This is how we do dynamics. Where is the meat in this process? Where is the essential principle? It's indeed F equals ma, right? That is enabled all this analysis. F equals ma is the fundamental principle. So Navier-Stokes equations is nothing but F equals ma, right? F equals ma in everything. We use F equals ma to design airplanes and to shoot rockets and to predict how a tree leaf will fall, to predict how the heart will beat, to predict how the viola string will vibrate. Everything is F equals ma. But the thing is that it's not mathematically proved. F equals ma is not mathematically proved. This is a little bit scary. The principle that we use in every nook and cranny is not mathematically proved. And this actually implies that it's not right all of the time. Yes, indeed, it's not right all of the time. It fails in the very large scales and in the very, very small scales. We're going to talk about that later. Okay. Newton also did composition of forces, like Aristotle did composition of motion. Now it's composition of forces in the exact same way. And he is very famous of his universal gravitation, right? So he analyzed the problem of, we call it central force problem. So a body that is revolving around another body, and there is a force that is always pulling it, like a centripetal force. This is what we call central force problem. So first he proved Kepler's area law, and using geometrical argument, there is no dynamics in there. Then for a circular orbit, he said, okay, this is straightforward. Gravity will provide the centripetal force, and you will just move with a constant velocity. This is straightforward. And for the elliptical orbit, now it needs serious analysis. He used geometry. He accepted Kepler's laws, Huygens' equations for the centrifugal or the centripetal force, all together to come up with the universal gravitational and the inverse square law, GMM over R squared, his celebrated thing. Because remember, these were very well known to his contemporaries. This is not his original contribution. He just organized things. And in fact, if you read the Principia, you will find his words. These concepts are known to the geometers of the time. Okay? But this is his original contribution, and I want to stress here, look at this. This is indeed combination of the efforts of others, right? We need to read the work that people did. It's an interesting quote by René Dugas that the fall of an apple did not suffice to give Newton the idea, okay? It has a very long history of development, and he has like 4 pages quoting people and demonstrating the long history before universal gravitation of Newton. It was interesting to me to know that Hooke actually wrote down the law. That gravitational force is proportional to m and over r squared. He formulated the law and discovered the square of the r. And this is well before Principia, 1687 Principia, okay? But the point is, to justify this thing, you need the concept of centrifugal force, which Newton benefited from Huygens. And more importantly, he verified it experimentally. This is the point. So look at this experiment. This is interesting. By measurement, measurement even by others. Look at this. Well, the moon orbit, the radius of the moon orbit, is around 60 times the Earth radius. So this means if the force goes by 1 over r squared, the force, the gravitation of the Earth onto the moon is 1 over 3600, that on the Earth, right? And if you just leave this object to fall down on the Earth here, it will fall about 15 Paris feet in 1 second. We can know that. Divide this guy by 3600, you get that how the moon will fall off. What do you mean by fall off? Well, because if it's not revolving, if it's not being attracted to the Earth by a centripetal force, it would go in a straight line. So if it would go on the curve, then we can measure this distance and see how it changes. And when he did that, he found 1 over 23 poos. If nowadays I'm analyzing something as big as that, and I'm expecting 20, I got 23, I would just call CNN right away to do a press release. This is a finding, but he believed that this is not accurate enough and actually gave up the idea. After 16 years later, 16 years, just giving up the idea, at one of the meetings of the Royal Society, he learned about Pickard's measurement, new measurements of the Earth radius. When he took the new radius, he found the 1 over 20 poos. And here is the celebrated universal gravitational law by Newton. Newton himself said that, if I have seen further, it's by standing on the shoulders of the giants. So, and you can see it in his make use of Galileo's principle of inertia, Huygens' concept of mass and centrifugal force. Kepler's laws and the inverse square law by others. So he combined all this into an organized corpus of mechanics. So this is why some people, like I said, they debate the great honor that he got. Right? We named the field after him, Newtonian mechanics. So people say, no, it shouldn't be Newtonian mechanics. It's many others, right? And even the thing that we keep using all the time, F equals ma, he did not write it in its exact form, like what we're applying nowadays. Anyway, so after Newton, everything was really organized now. We just need a little bit more of calculus and we're done. So almost a new branch started to show up, which we call analytical mechanics. And one of the essential objectives of this course is to see the difference between Newtonian mechanics, how we apply F equals ma, and something called analytical mechanics, that there is no vectors at all, no vectors, no force, no acceleration, because it's a vector, no linear momentum, it's a vector, no vectors, it's just scalar quantities, energies, okay? This is analytical mechanics. You can say it started with Leibniz, although we can trace back. Let's start with Leibniz. He was contemporary to Newton. And like I said, the force is an arbitrary concept. You can define the force in your own way. So for him, he said, look at this. If I want to lift an object, weight W, for a distance h, these two quantities really matter, because I would exert more force in his language if the weight is increased or the distance is increased. So to him, the force was the multiplication of the force of our force with the distance. To him, the force was our work. And he said, if I define the force this way, then it cannot be change of linear momentum. It cannot be. Why? Because, okay, consider this example. If you have a body with weight W, just fall down from a distance 4h, it acquired during this journey, during this excursion, some weight, some force, right? That actually is sufficient to carry you over to the same height again, right? So during this excursion, this body acquired the force that is 4wh, which is the same if you have a weight 4w from a height h, okay? This is the same acquired force by his definition. Now, these two motions, they will acquire different linear momentum. We already know that this guy will acquire different velocity than that guy, and the relation is 2, so it will not go right. So it cannot be change in linear momentum. These two things will go down by different linear momentum. So what it should be, he said it should be mv squared. Yes, because, the velocity square goes with the height. So he came up with the concept of vis viva. This is the Latin version of it, so it's the living force, which what we know by what? The kinetic energy, right? This is twice the kinetic energy. Okay, our kinetic energy is Leibniz vis viva. So in nowadays language, his equation of motion was his, remember for Newton, there is a cause for the motion, which we call the force. And there is the result, which is the acceleration. And Newton just related these together. This is the essential equation of motion. How the cause is related to the effect, right? So the force is equal to the change in linear momentum. This is Newton. Now you're defining the force in a new way. That's okay. You have to tell us how this force is related to the motion. So he's saying that my force is the change of the vis viva. Both are correct, right? Both are different ways of solving the same problem. But Newton is complete because it's vectorial. This guy is not complete in the following sense. If you have an object in three-dimensional space, how many degrees of freedom? We have 3. Okay, Newton's equation, how many equations? It will provide you 3, because F equals ma in each direction. So it's sufficient to analyze the motion. How equation will you get out of this guy? It's always 1. It's always 1, right? Scalar equation. So it's not sufficient. can be sufficient in some very special cases, but it cannot serve as a general principle in mechanics. And we'll come back to this later. I'll have to speed up a little bit. Euler, he really did the necessary calculus to us, and you can see it from his work. He really wrote this. So the force dt is mdv, so he almost wrote F equals ma. And you can say that this is a definition of the impulse, right? The impulse changes linear momentum. He tried to turn mechanics into a rational science, not just an experimental science. And this is a very interesting thing. He said, okay, this is the rule, right? We know that it's true, but I'm not only concerned with proving that it's true, I am concerned with proving that it's a necessary truth, in the sense that the change in the linear momentum cannot be identified with the force squared or force cubed. It has to be identified with the force. These rules, if they were exist, they have to imply a contradiction. This was his way of thinking, which is very interesting. And my favorite part, Maupertuis. So Maupertuis, he's a French scientist, as the name may tell, and he came up with something. He was a metaphysician in addition to being a mathematician. So he came up with a metaphysical principle that is so beautiful that we can, I think it's well described by a quotation from the Nobel laureate Feynman. So Feynman was in his high school sitting bored from classes. And the high school teacher came to him saying that, Richard, come, I will show you something interesting. So all the way later on, Richard Feynman was giving a plenary talk because he won the Nobel Prize. And he said that. He quoted that incident with the teacher, okay? Richard, come, I will show you something interesting. He referring to this something interesting. Then he told me about something which I found absolutely fascinating and have since then always found fascinating. Every time the subject comes up, I work on it. In fact, when I began to prepare this lecture, I found myself making more analyses on the thing. Instead of worrying about the lecture, I got involved in a new problem. This thing was the principle of least action. So this guy said, wait a minute. Nature must be doing things in an optimal way. Nature is wise, must be doing things in an optimal way. This motion may be moving under the law F equals ma or whatever, but while moving, it must be moving while minimizing a certain magic quantity. So he believed that there is a magic quantity such that all these motions happen to minimize this magic quantity. Still, it's a metaphysical principle because, okay, I can agree, but what is this magic quantity, right? You have to tell me. The point is, if this magic quantity is found, now the whole discipline of mechanics is turned into optimization. Because if we want to solve a dynamics problem, instead of going and just trying to write down the equations of motion, we will go and find the trajectory that minimizes this quantity. It's completely an optimization problem, right? So he said, well, if I want to move a body, m, so the larger the m, the more action I need to provide. And if I want to move it with a velocity v, again, the larger v, the larger the action. And if I want to move it to a certain distance d, the larger the action. So he said, he defined a quantity called action. The action needed to execute the motion. And he said, nature must be doing things efficiently. Nature must be minimizing this action, the integral of this quantity over the motion. mv ds is minimum, And if you manipulate this a little bit, you get mv squared dt. So the kinetic energy, the integral of the kinetic energy, or Leibniz vis viva, over the motion is minimum. This was his principle, which was a metaphysical principle, but he successfully applied it to impact, got very interesting results that people did not know before. Of course, there is a very long chapter in the history of mechanics about the polemic, the quarrel about this principle, because at that time, Galileo was very experimental, right? Actually, Galileo has a very interesting quote, I hope I can remember it, about Copernicus against Aristotle. He said something like, if he dared to be against Aristotle, it's because the telescope, it's because the telescope had given the astronomer eyes 30 times the capability of a philosopher. What I'm trying to say is that these guys exerted a lot of effort to emancipate the science of dynamics from philosophy to be a science of facts, truth, experimental truth. And you come now to say that, okay, nature, God, and all these, concepts that sometimes are scary to people. So it's a metaphysical principle. How did you come up with this principle? So they fought so much that one of the professors actually returned his diploma to the Academy of Berlin when this guy was the president. So you can read a lot in history about the fight against this principle of least action. Luckily, when Euler and Lagrange came up with the necessary calculus, which we will have in this class, the calculus of variation, they showed that indeed this quantity, it's not minimum, but it's either minimum or maximum, okay? So the first derivative, or what we call the first variation, is 0. And it has to be subject to conservation of energy. Later on, Hamilton came up with the general principle of least action, saying that it's the first derivative of this integral that is 0, and this integral is not only kinetic energy, but kinetic minus potential, subject to no constraints. So this is in a glance, the history of the principle of least action. Interestingly, Newtonian mechanics fails in the very large scales and very small scales. The principle of least action remains valid in the spectrum of very large scales, small scales, and our scale. I'll just skip D'Alembert. Lagrange, I would say the mechanics that we know nowadays, we really owe to Lagrange. The language that we write and how we solve problems and everything, he crowned all the efforts. And he really made it systematic, and he codified all the principles. So if you want to read something, just one thing in mechanics, then it's Lagrange Analytical Mechanics book. At the beginning of the thing, like I said, he came up with a very systematic way of solving the equations of motion, which will be the main focus of this course. So one of the objectives of this course is that, Newtonian mechanics is very hard, by the way. It's very challenging, very tricky. I can assure you, given any illustrious professor in mechanics, we can try to come up with a problem that tricks him or her. I mean, for sure you can trick me with the problem in Newtonian mechanics, but it's almost impossible to trick me with a problem in Lagrangian mechanics, because I just turned the crank. In Newtonian mechanics, there are many things to worry about and to take care of, whether the frame of reference is rotating or not. These are vectors that you're dealing with. It's very hard, and you can be tricked. How these bodies interact with each other. Like we have problem in our research, like we were analyzing the flight dynamics of an insect. So we have the wings goes back and forth, and the insect move with its 6 degrees of freedom. This is a very challenging problem. If you try to write down the equations of motion with Newtonian mechanics, good luck. I would be very proud of you if you do it. With Lagrangian mechanics, I don't even think about it. It doesn't make any difference if it's a 6 degree of freedom body with another 3 degree of freedom body attached to it, or just a ball sliding on a plain. I mean, it's the same procedure. I turn the crank. So this is why Lagrange in his work at the beginning said, no diagrams will be found in this work. I mean, if you solve in Newtonian mechanics, the very first thing is free body diagram, right? And if you got it wrong, everything is wrong, right? So this guy said, no, you don't need it. It's just algebra. Turn the crank. This will be the main focus of our course. So after the course, hopefully, if you have any problem in dynamics, no matter how hard it is, it doesn't matter. You can just solve it like this. You can even program it. Program a way to write down the equations of motion, because it's algorithmic, it's algebra. So by this time, scientists thought that dynamics is almost perfect. Yeah, it's really, I mean, like I say, now we can solve it either Newtonian or Lagrangian. Give me any dynamics problem, I'll solve it. And it's a deterministic science. There is no probability. If you give me a force, I will tell you in 1 second this object will be exactly here. It's a deterministic science. So mechanics people were very proud of their science. And it's almost perfect after Lagrange. Then, in the early 20th century, there is a double revolution that told us that it's neither deterministic nor correct. Your Newtonian mechanics, first of all, time is relative. Time is not absolute, which this principle, time is absolute and runs uniformly, is the main principle of dynamics. If you destroy it, then Newtonian mechanics fails immediately. So Newtonian mechanics is not correct all of the time, at least. This was Einstein special and general relativity. And then we have the quantum mechanics that stopped our bragging about the science being deterministic. It's no longer deterministic. This was huge shock that some people thought of it as a scandal, because we had been building this corpus of mechanics for about 2,000 years, and it came to almost perfection. And now, just look at the dates here. It's so close to each other. You ruin it in the very large scale, and you ruin it in the very small scale. What? But remember, this is the very nature of our science. I mean, that's fine. I will just finish with this. So this is the history of mechanics, the Hellenic period, Aristotle. Aristotelian mechanics, because of the prejudice, about 2,000 years. This is classical mechanics. You can say Newton and Lagrange. Classic Newtonian mechanics and Lagrangian mechanics, which we will study in detail in this course. And then the double revolution, relativistic mechanics and quantum mechanics. If you look at this actually and try to make a fit to see what is so this is the first thing that we got, the second, the third. So where will be the next revolution? It's very close. First of all, I admired MATLAB when he provided me with this parabola that fits these things. Why? Because it shows that we're going down. Yes, we will always be going down with prejudice. Okay? And the next thing will be by the end of this century. And by the way, this is not speculation. Why? Because the double revolution are not compatible with each other. Relativistic mechanics is not compatible with quantum mechanics. So yes, there is room for a new revolution. This simple formula says that it's by the end of this century. So try to be part of the glory. I will skip this because this is this is exactly our course. We will spend too much time with it. These are the main references. I will provide a syllabus on EEE, okay? The first two books are the ones that I will. There is no required textbook. You're not required to get any textbook. You can rely 100% on the lectures. But if you want to keep one book on your shelf, then I recommend one of these two. If you feel like you're not really familiar with dynamics and the undergraduate concepts and you need something that has colors and an undergraduate-looking book, then it's the second, though it's expensive. This guy is the one that I use all of the philosophical ideas. It's very interesting. These are other references. Grading, 40%, homeworks and quizzes, midterm and final. One thing, there are pop-up quizzes. So you will come just in a regular lecture like this, and at the end of the lecture, we'll have a quiz. So we'll have about 4 or 5 of these quizzes over the quarter, and they account for half of this, so 20%. So each quiz is like 5%. This is really precious. Don't panic, these quizzes are for facts only stated in that lecture. So if you just pay attention, and there will be open book, open notes, so don't worry. But you have to be there, which means that if you intend to miss a lecture, let me know any time before the lecture so that I give you the chance to compensate it. If you don't let me know, I will not be able to give you a chance, okay? I think that that's it. Do you have any questions? So we finished 10 minutes early. That's good. Any questions? Please.
Are we able to get this PowerPoint?
Oh yeah, I will post this, and I will post the syllabus on EEE. One thing, I don't have notes. I will write on this. This is the only time, the only lecture that I will use PowerPoint. I will use this guy, and you will have to write after me. So yeah, sorry about that. By the way, this is a good thing. Last year, we recorded all the lectures. So if you miss a lecture, so if you can type here, our website, the research group. Oh, where is it? Yeah. Our research group, there are courses here. These are the courses that I usually teach. You can say 241 dynamics. Here is the recording of all the lectures of the last year, which is pretty much the lectures of this year. If you miss a lecture, you're more than welcome to go and watch it, okay? The first lecture, though, will be a little bit different. Every year you read more a little bit about history. Change your opinion, okay? Any other question? Any question? Okay, guys, see you next time.